So, this part of the lecture we would like to talk about workflow. So basically last time we considered which machine learning problems or which machine learning approaches we can use to solve a problem using our data to build our model. In this case, we will consider how we can build a model in a very structured manner. In this case, we consider workflow proposed by Amershi et al. In several years ago. And this particular workflow is some sort of compromise between very simple workflows, like for example CRISP-DM, or very overcomplicated or very professional ones, like for example proposed by Microsoft, where you have every role in this workflow predefined and you have various steps. They are also very well defined, but for small teams, so for a single man project, it might be very overcomplicated. So that's why we stick to this one. And yeah, let's start with the first stage. So the first stage, before we build any model or even collect the data, we need to define what this model should do. And this first stage is called model requirements. During this stage, we need to define what this model must do for us. So we define which features might be relevant, whether there is an output or there is no output, for example, if you are talking about unsupervised learning. So in this case, we define which model it should be, which type of the machine learning problem we would like to solve. Then, after that, the second stage would be to collect our experience, to collect data, so-called data collection, where we define, we already defined which relevant features might be relevant, and then we need to collect the data for them, as well as labels if we're talking about supervised or semi-supervised learning. It does not mean always that you are the only one who will collect the data. In some cases, for example, especially in computer vision cases, there are quite a lot of data sets that are already publicly available. You can download and use to build your model or to extend your model, for example, by means of transfer learning. And similar, you can use, for example, other simulation models, for example, flowsheet simulators, to collect data set that will be used together with real plan data to build your final model. The next step after we collected the data, we need to complete data cleaning. So we start preparing data. What do we do during data cleaning? So during this step, we need to define whether there are outliers, for example, errors in our data, and then either we can remove these examples from the data sets or we can try to correct them. The next step, after we have our data cleaned, it's a so-called data labeling. In this case, if we still do not have labels for our data, I mean, for example, we did not collect them, during this stage, we must be sure that at the end of this stage, we have these labels if we are talking about supervised or semi-supervised learning. Then we start to work with data. Before we can fit the data into our model and start training process, it's also recommends, or for some models, it's necessary to run feature engineering. What does it mean? So basically, feature engineering consists of two major steps. One of them is so-called feature selection. And the second one is feature transformation. During feature selection, we need to define which features might be relevant for our use case, for our problem. How we can do it? There are different ways. The simplest one of them would be that we just try to carry out a correlation analysis. And we try to define if there is any correlation between our output, between our label and the selected feature. If there is a correlation, then we can consider this feature further. Feature transformation, it's something that some models require you to do. So for example, it might be scaling. When you, for example, if you have your temperatures from, let's say, from 273 to 373, but at the same time, you have another feature, for example, pressure from 0 to 1. And in this case, to make the training process more efficient, in this case, we need to scale our features. In this case, to make them, for example, from 0 to 1, both of them. For sure, we save the scaling coefficients and then we can transform it back at the end. But for the training process, it's advised to scale your features. For some models, for example, for neural networks, it's advised not only to scale your features, but so-called normalize them. That means that at the end of this routine, we get our features normally distributed around 0. So at the end, they will be between -1 and 1. Then, after that step, after feature engineering, let's say data collection till feature engineering, as output from this, we have our data set. After that, we can for sure split it into training data we use for training data, and also, for example, for validation, another data set with other samples with the same distribution. But after feature engineering, we have our data set we can use to train the model. And that's exactly the next stage, model training. Model training, if you're talking about traditional machine learning approaches, it's something when you try to find the free parameters of your model. So if you have, for example, regression, then you have the parameters in front of each of the features. And those are exactly the free parameters you would like to find, you would like to fit for your model by using the data. So in other words, it's also optimization problem, and it's also fitting. During model training, as I said, we find the parameters, we train the model, we find the model, and we have the model at the end. So the output of this step would be trained or fit model. Then we need to evaluate our model. We already talked about so-called loss functions or target functions we use to optimize, to find the parameters, but there are also metrics. So those metrics help us to assess our model in a better way, like more comprehensible. In this, that's the next step, model evaluation. And it's exactly where we use also our validation or test data. After we evaluated our model, we can decide whether it's something we expected, something we defined during model requirements phase, and if yes, then we can carry on and we can deploy the model. And it would be exactly the next step, model deployment. What is model deployment? Yes, simply model deployment and nothing more than you use the model for a specific problem. For example, you have your plants and you have your control system, and then you connect your model with inputs, so with data coming from sensors and outputs that the model can interact with your system in some way you can define. And then, so model deployed. And as the model runs, you can also monitor your model. It's similar to model evaluation, but in this case, you use real plant data and you evaluate the model that is already deployed. Why it's important? Because some models, for example, or some processes can change over the time. And in this case, it's important that you have your model up to date. And how you can do it? You evaluate your running model, you monitor it, and as soon as it degrades, you can replace it or update it. And that's why we have also some feedback loops here. So basically, as soon as we find out that our model does not run as we would like to anymore, we can start the whole process all over. For this, for example, we can collect new data and we can run the same workflow until the model deployment, and the next iteration we can also monitor the model and all over again. There are also additional loops, for example, from model evaluation. In case our model quality is not that what we expected, we also can try to recollect the data, or we can, for example, only try another model. So it's basically also another large feedback loop where we can go back to any of the previous steps and modify something in order to get better results.